Hi everyone, welcome to our video on how to do a two-sample t-test in R. Up top, I just want to remind you that this video is going to assume that you already understand the theory behind the t-test and sort of statistically the math that's going on there. It's also going to assume that you have some familiarity with R and importing data. So if you don't have that knowledge, go ahead and check out some of my other videos on how to do those things. But assuming that you do have that knowledge, this is really meant to be kind of a refresher or a quick and simple introduction to the actual functionality of how you can do a two-sample t-test in R. Also, down in the video description, I'll include a link to the script file that we'll be using, which is available from my GitHub repository. Okay, so we're going to be using the same data set that we used in the one sample t-test example. So just as a reminder, we're going to import our usual set of libraries. Then we're going to read in these data from the web. They currently live on my GitHub repository. And just to take a look at the first few rows of the data, again, these are some fictional data from some students who either took an SAT prep course or did not take an SAT prep course. And actually, let me go ahead and rather than just looking at the head of the data, let's look at all of the data because this data set isn't too big. So you can see we have observations from students, 20 different students, 1 to 20. Each student was randomly assigned to either take the prep course or not take the prep course. So we have independent observations here. These are people who didn't have any kind of relationship to each other and were randomly assigned to these different groups. And then we have their SAT score on the SAT math section. And as I think I mentioned in the last video, this is an old example, so I'm not even sure that the SAT math section has scores in this range anymore. I think they've changed the scoring. But I think if you took your SATs around 2007, this is how they were scored. To get a quick summary of those data, beyond just looking at the tabular representation, we can use the plot function to get a box plot using base R. So you can see then it's going to draw a line at the median of each group. So that thick dark line is the median. The box highlights the interquartile range. And then the whiskers are drawn out to the last observation within, I believe it's 1.5 times the interquartile range. So in this case, we don't have anything that really lies beyond that. If we had some outliers, they'd show up as their own individual dots. But just to orient you to the plot function, right, the thick bar is the median. These would correspond to the 25% and 75th percent, or 25th percentile and 75th percentile. And then the whiskers are going to be drawn out to the last observation within 1.5 times the range. So they're not drawn out to 1.5 times the interquartile range, obviously because they are asymmetrical. They're drawn out to the last observation. So if this line cuts off here, then that means we didn't have any more observations beyond that point. Now, if we just want to do a regular two-sample t-test, we can use the t.test function. And now we're going to critically add in our dependent variable as a function of the factorial independent variable that we have. And we're going to assume that we have equal variances, at least to start with. That's an important assumption, right? It's going to be key to check that. And sometimes we might want to adjust for that. But if we assume that we have equal variances, then this is what we're going to get as a result. You can see we've got a two-sample t-test here. The data show us SAT by group. The t-test, or the t-value in this particular case, happens to be 2.096 with 18 degrees of freedom, and that is a p-value of 0.05048. So if we were doing a strict hypothesis test here, in sort of the Nyman-Pearson sense of hypothesis testing, this would not be a statistically significant result if we set alpha at 0.05. Because remember, if we set alpha at 0.05, then it's less than 5% of the time we really want to, if we really want to control that type 1 error rate. So in this case, this would not be statistically significant. It is, however, still a reasonably surprising result under the null hypothesis, right? The difference between this and, say, 0.049 probably isn't all that much. So depending on sort of the statistical testing framework that you ascribe to and how concerned you are about type 1 errors, that might affect how you're going to interpret these data. It's also going to return for us the 95% confidence interval of our difference. So critically, this isn't the 95% confidence interval of any one group. This is the 95% confidence interval of the difference. And you can see that confidence interval just barely includes 0. Hence, it's not statistically different from a null hypothesis in which we assume 0 as the true value of the difference. It's also going to return to us the means in both our course group, which happened to be 605, and the no course group, which was 577. Now, as we said, we might be interested in different types of tests or variations on this idea. So for instance, we could do a minimal effects test in which we assume a non-zero null hypothesis. So for a non-zero null, we might, for instance, be interested in a 20-point difference. Can we say that the course actually improved your performance by 20 points or more? And if we do that, you can see it actually changes our result pretty substantially. The t-value has gotten a lot smaller, right? And our p-value has gotten a lot bigger because the difference between our groups, which is only about 30 points, was not even statistically different from 0. So it is even less different from 20, right? So if the true mean were 20, not assuming a true mean of 0, but if the true mean were 20, it would not be uncommon to observe a mean difference this large or larger about 56% of the time, right? So this would not be a surprising difference if we thought that the true difference in the population was about 20 points. We could also approach this, right, depending on what our hypothesis test is, using a one-sided test rather than a two-sided test. Because we might not just be interested in if they are not equal to each other, but if a difference is specifically greater or less than a certain value. So, for instance, if I wanted to see is the difference specifically greater than 15, I could specify that mean in the t-test function. And then I could say that the alternative is equal to greater. Because again, the way that the t-test function works, you specify what the alternative hypothesis is, not what the null hypothesis is. But if I say alternative equals greater, then that is mathematically the same as a null hypothesis where I assume that the true mean is less than or equal to 15. So if we do that, right, you can see that the p-value has gotten a little bit smaller, and there's two reasons for that, right? One is we're looking at now 15 instead of 20, so our mean difference was more different than 15, and it was less different from 20. And the other thing is that we have a directional hypothesis here. So we're specifically assuming that the true mean difference is less than or equal to 15, and this is somewhat unusual if that were true, but we would actually observe a mean difference this large or larger about 17% of the time if that were true. We could change this value again if we actually wanted a null hypothesis test against 0, right? We could do a one-sided hypothesis test setting the mean to 0. And now what you'll see, right, is that initial t-value that led to a p-value right at the 5th percentile is now 0.025. And this could be reasonable in this situation because you're specifically interested in if the course makes these students better. You would assume that the course is not going to in some way make these students worse because they're just getting their general education in the no course group. So the addition of the course, you might be able to justify making a directional prediction, which in this case then makes it more statistically surprising, right, that you're going to observe the difference you did. Because if we assume that the true value was less than or equal to 0, rather than simply equal to 0, now we're only looking at one tail of that probability distribution, and our p-value has been cut in half. So again, that's just to show you kind of the functionality of the t-test function, that you can assume different mu's, you can make different types of hypotheses, but ultimately you don't want to just play around with this until it gives you the result that you want. What you want to do is actually pick the one that makes sense given your hypothesis. The other way that we can approach this is to actually use the linear model function, or LM, to do this within the regression framework. Because if you've watched my other videos on statistics, right, the t-test, ANOVA, all those things, they aren't actually different from regression. They are just special cases of regression in which you've coded your variables in a certain way. So remember, everything is always a linear model. There's always a linear modeling way to approach whatever question you're asking. So we can create a linear model looking at your SAT scores as a function of group, like we've done here. And then if we print a summary of that linear model to the screen, you see that it's going to return a bunch of different pieces of information. Because this is a linear model, it's going to give us both an intercept and a slope here. But most critically, it's going to give us the same t-value that we had before when we first ran that t-test function. And of course, because the degrees of freedom are the same, it's also going to give us the same p-value that we had before from when we first ran that t-test function. So, whether you use the t-test function or whether you use the linear modeling function, that's entirely up to you. And maybe dependent kind of on what you're familiar with, you might approach it one way or the other. Personally, I like to do everything within the linear modeling framework as much as possible. And you can see this also gives us a lot more useful information when we actually print the summary of the linear model to the screen beyond what we would get when we just did the t-test function. So the next thing that we want to do is actually look at some ways of visualizing these data. So first, we can actually create some box plots where we're going to look at the distributions as a function of group. So this is very similar to what we got from base R when we were just using the plot function. But now we're going to use the geom box plot function inside of ggplot in order to get our SAT math scores on the y-axis. Then we're going to have students who took the course and students who did not take the course. And then otherwise, these box plots are interpreted in exactly the same way as they were from the plot function in base R. We have the median as the thick center line. We have the interquartile range as the box. And then you have whiskers drawn out to, I believe it's 1.5 times the interquartile range. The next type of visualization that we might be interested in is actually plotting the means of these different groups with some error bars. So that's here on lines 61 to 77. And again, you can follow along with this and kind of dissect it in the script from my GitHub repository. But the main thing that we're using here are this geom error bar and geom point in order to draw upper and lower limits that are one standard deviation above or below the mean in each of our two groups, and then a dot that represents the mean of each of those groups. So now we can see the mean and one standard deviation above and below that mean. If we wanted to actually draw a visualization that corresponds a little more directly to our statistical test, we could draw the 95% confidence intervals around our two data points. So this is identical to what we did in the one sample t-test video, but now we're doing this with multiple groups. So we're ultimately going to get some data that show us the means for the different groups. But what we're going to do now is rather than draw the 95% confidence interval of the course group and the 95% confidence interval of the no course group, what we have done is calculated the difference between those two groups. Then we can also calculate the standard error of that difference and the 95% confidence interval of that difference. So you could draw confidence intervals around your two group means, but if you actually want to create a visualization that more directly corresponds to your hypothesis test, it's actually going to be really helpful to plot that difference. So that's what I've done here. So you can see we have a mean difference of about 28. But the lower limits go down to just below 0 at negative 0.06 and up to about 56.1. Right? So this does not exclude the null value of 0, nor does it exclude our prior null value of 15 that we also put in there. If we wanted to change this null value back to be 0 again, I can adjust the H line in this graph. And now you can see, aha, yes, this was not a statistically significant result, but this is a really excellent example of why something not being statistically significant is not evidence of no difference. We can't rule out 0 as a difference, but we also can't rule out that our course might improve people's performance by as much as 50 points.